On November 7, 1940, the Tacoma Narrows Bridge made history for being one of the most dramatic failures in bridge engineering.
The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing.
This $135 million bridge stood for just 4 months before it came crashing down, and all because of a single design change meant to save some money. This small decision caused the bridge's roadway to twist and turn until it finally broke apart and plunged into the water below. This disaster changed the way engineers design suspension bridges forever. Hi, I'm Wilson Khan, a civil engineer working in New York City, and in this video, I'm going to tell you the story of how the Tacoma Narrows Bridge collapsed and explain the forces that caused the deck to twist and turn so violently. In the 1930s, people began to realize that the Tacoma and the Kitsap Peninsula needed a direct connection. Puget Sound, this huge body of water, had always made travel between these two areas difficult. If you wanted to get from the Tacoma to the peninsula, you either had to take a long detour by road or hop on a slow ferry ride. But as the region grew, so did the demand for a faster, more convenient route. So the idea of building a suspension bridge came to life, a bridge that would not only improve travel, but also boost the local economy. But building this bridge wasn't easy. The Great Depression made money tight, and the engineering challenges of spanning the wide and deep Tacoma Narrows were tough to overcome. It wasn't until the late 1930s that the project started to move forward thanks to support from the federal government and the military. The Washington Toll Bridge Authority asked for $11 million to build a bridge, but they needed to cut costs. Enter Leon Mosep, famous engineer who came up with a cheaper and innovative design. His idea, a sleek, lightweight suspension bridge using plate girders instead of the more traditional trusses. This design was cheaper, but it also made the bridge behave in ways people hadn't expected. As the bridge was being finished, workers and engineers noticed something strange. It started to move up and down, especially on windy days. This unusual behavior earned the bridge the nickname Galloping Gertie because it looked like it was galloping in the wind. While it was interesting to watch, it was also pretty alarming. Engineers tried all sorts of fixes like adding hydraulic buffers and securing cables to big concrete blocks, but nothing seemed to work. On July 1st, 1940, the Tacoma Narrows Bridge finally opened to the public. It was a big moment, a celebration of modern engineering, and a new way to connect the region. Thousands of vehicles crossed the bridge that day, and many people admired its sleek and elegant design. But as drivers crossed the bridge, they felt something they didn't expect. The bridge didn't just sway a little bit. It rose and fell dramatically, making some drivers very nervous. Then came November 7, 1940, a day that seemed like any other. The winds of the Tacoma Narrows were strong, about 42 miles per hour, but nothing unusual. As the morning went on, the bridge started to sway like it usually did, but this time the movement got worse, and the twisting motion began. By 10 a.m., the bridge was twisting violently, with one side rising while the other fell. Drivers on the bridge were in a nightmare, as the road beneath them twisted and buckled. Everyone managed to get off the bridge except for one person, Leonard Coatsworth. A local newspaper editor found himself trapped on the bridge with his dog, Tubby. He had to abandon his car and crawl to safety, leaving his dog behind. At exactly 11 a.m., the middle section of the bridge finally gave way. The massive steel cables snapped, and the roadway plunged into the water below. The collapse was caught on film, creating one of the most famous engineering disasters ever recorded. Luckily, no one died, but the collapse left a huge impact on the field of engineering. Right after the collapse, engineers and scientists from all over the world tried to figure out what went wrong. Official investigation pointed out a few key issues, including how flexible the bridge was and the fact they didn't test it in a wind tunnel. So, what caused the Tacoma Narrows Bridge to collapse? The answer is a mix of aerodynamics and structural engineering. The bridge's design was innovative, but it had a major flaw. Using plate girders instead of trusses made the bridge aerodynamic, which increased the effect of the wind. This made the bridge vulnerable to something called aeroelastic flutter. When the wind hit the bridge, it started creating swirling air currents that made the bridge twist. This twisting got worse and worse until the bridge just couldn't handle it anymore and collapsed. To put it simply, the bridge started with up and down movements, which then turned into twisting. As the wind and gravity fought against each other, the twisting got stronger until the bridge finally gave way. Today, engineers are much more aware of these kinds of issues, and wind tunnel testing is now a standard part of designing bridges. The collapse of the Tacoma Narrows Bridge taught engineers valuable lessons about the importance of considering wind effects in bridge design. Since the collapse, bridge design has come a long way. Modern suspension bridges are built with aerodynamics in mind. For example, many bridges now have streamlined decks that let the wind pass through or around them easily. On some bridges that have finger joints like the Verrazano Bridge, you can actually see the joints moving with the entire bridge deck because of the high winds. I actually did work on the Verrazano Bridge myself for a short time, and on the George Washington Bridge, I saw the finger joints being replaced at night. By testing models of bridges in simulated wind conditions, engineers can find and fix potential problems before construction starts, making sure new bridges can handle the forces that took down the Tacoma Narrows Bridge. Aeroelastic flutter isn't just a problem for bridges. affects all kinds of structures like airplane wings and tall skyscrapers. Engineers have come up with different ways to deal with this, like changing the shape of structures to reduce drag or adding dampers to absorb the energy of the oscillations. In 1950, a new Tacoma Narrows Bridge was built on the same spot where the original one once stood. This time, the bridge was designed with the lessons of the past in mind. The new bridge had deeper trusses, better aerodynamics, and was thoroughly tested in a wind tunnel to make sure it could handle the forces that brought down the first one. This new bridge has been standing strong ever since, and in 2007, a second bridge was added to help with the traffic congestion on the original one. Now, the new bridge carries eastbound traffic toward Tacoma, while the 1950 bridge handles westbound traffic heading toward Gig Harbor. The story of the Tacoma Narrows Bridge is now a key part of engineering education, showing up in textbooks and case studies about aerodynamics, structural dynamics, and material science. It's a powerful reminder that even the best engineered projects can fail, and that those failures can teach us valuable lessons. If you enjoyed this story about the Tacoma Narrows Bridge class, be sure to check out my other videos on engineering marvels and disasters, and don't forget to like and subscribe for more in-depth engineering stories.